Okay, so I'm Robert Haas, and this is my talk on unlogged tables. It's a pretty short talk, so if you hate it, you won't have to hate it for very long. This is one of the features that I developed for PostgreSQL 9.1, and so now I get to talk about what I did and why I did it, and hopefully it'll seem useful to at least some of you. So here's the big picture. PostgreSQL, like most other databases, has something called a write-ahead log, and we rely on the write-ahead log to provide a number of features, including crash safety and replication. Sometimes you don't need those features. Sometimes, in fact, not needing replication is pretty common. Many people don't need replication. They have other ways of backing up their data. Maybe a nightly backup is enough for some people in what they're doing. Not needing crash safety is a little bit more unusual. Usually you don't want your data to go away if the system crashes, but sometimes you don't care. So unlogged tables are for the times that you don't care. What you're giving up is crash safety and replication, and what you're getting in exchange is improved performance. So I'm just going to explain exactly what that means. First of all, unlogged table data is not replicated. The table does exist on standby servers. The schema is there, but you cannot access the table on a standby server. If the standby is promoted to a new master, the table will then become accessible, but it will be empty. There won't be any data in it. And on the master, unlogged table data does not survive a crash. That could mean an operating system crash, like somebody pulled the plug or the kernel panicked. That could mean a PostgreSQL crash, a backend seg faulted, or anything else that causes a PostgreSQL crash, or an immediate shutdown. You can actually tell PostgreSQL to crash on purpose. We call that an immediate shutdown. Don't get fooled by the nice name. An immediate shutdown means please immediately crash. And so that is the same thing as a crash. So in all of those cases, when you bring PostgreSQL back online, the database system will enter recovery, and all of your unlogged tables will be truncated. Because there is no guarantee that the contents of the data file on disk are in any kind of remotely sane state. After a crash, we need some clean way to recover, and the only thing that really seems to be halfway realistic is to truncate the tables. So that's what we do. So on my next slide here, I have ventured into the realm of making charts, which is not something I'm real good at. But I took the risk. So this is an attempt to compare the different kinds of tables that we have in PostgreSQL. Of course, the type of table that you normally get when you say create table is a permanent table. And we've also had temporary tables for many releases. And now we have unlogged tables. And so this is sort of a compare and contrast between the different kinds of tables. The word logged on this slide is referring to the write-ahead log, not the server log. Okay? So the first row is our schema changes logged. All schema changes for all types of tables are logged. They are all written to the write-ahead log. Now, in the case of temporary tables, that might seem like a bad thing, because a temporary table is not going to survive a crash anyway. It's temporary. It's not even going to survive the end of the session, let alone a database crash. So you might say, you shouldn't be write-ahead logging those schema changes. And I agree with you, but that's not going to change anytime soon because it's an architectural limitation of Postgres that is going to take many years to fix, if in fact it ever gets fixed at all. So all schema changes are logged for all table types. Data changes, a different situation. In general, for permanent tables, data changes are logged because you need the data to survive a crash, and that's how you get crash safety. There is one exception here, which I've noted in a somewhat long footnote. If you're using copy, and you've created or truncated the table in the same transaction where you're using copy, and you're not using built-in replication, i.e. you have wall level set to minimal, then permanent tables will not need the data changes to be logged. Instead, we will just call fsync when the transaction is committed, which is often cheaper, at least if there's a large amount of data in the table. But in general, most data changes to permanent tables have to be logged in order to provide crash recovery, and that's what we do. Temporary and unlogged tables both share the advantage that data changes are not logged. So what happens if we have a clean shutdown? Well, the permanent tables don't care. The data is there just exactly the same as it would be as it was when you shut down the database. Temporary tables are dropped because when a session ends, all temporary tables that belong to that session go away. Of course, when you shut down the database, then all of your sessions go away, which means all of your temporary tables go away. And unlogged tables, there's no effect. You can have data in an unlogged table, you shut down the database, you bring it back up again, data's all still there. Crash behavior. Permanent tables, again, no effect. That's the point of using a database that has crash safety. Your data should all still be there after a crash. Temporary tables, again, are dropped because they only last for one session. And unlogged tables are truncated. Okay? That's the main penalty that we're paying for using an unlogged table. We cannot survive a crash without right-ahead logging the contents of the table. Visibility, permanent and unlogged tables are both visible to everyone. They're visible to everybody in the system, while temporary tables are specific to one session. And one final note that I thought was kind of interesting, and people sometimes don't understand this. Permanent tables are processed by auto vacuum. Temporary tables are not. A temporary table's contents can only be accessed by the backend that owns that temporary table, and therefore auto vacuum and auto analyze will not process those tables. If those tables are only being if those tables are only sticking around for a short period of time and being used for trivial things, this doesn't really cause you a problem. If you're actually going to run complicated queries against them, you often need to manually analyze them from the back end that owns that temporary table in order to get good performance, and perhaps even vacuum them if you're really using them for a long time. So one of the nice things about unlogged tables is that because they are shared by multiple backends, they can also be accessed by auto vacuum, and auto vacuum will clean them up, trigger analyze to gather statistics, and do all that stuff just as it would for a permanent table. Yay. Any questions on this? People understand the behavior? Okay. So why would you want this? Well, I got a couple examples here. So sort of a canonical example is you might have a web application, and your web application might have a sessions table. If you lose the contents of your session table, then all your users have to log into your web application again. But databases don't usually crash very often, especially on Postgres. So you might not care, right? As long as you don't lose the contents of that table more than every once in a great while when something really bad happens, you won't really care very much. Maybe an even better example is caching. Sometimes you might use PostgreSQL to store a copy of data that exists durably somewhere else. So it's not that big a deal if you lose your cache because you can repopulate it. Another example, which I actually was inspired by something that one of the Heroku folks said to me yesterday, is ephemeral data. You might have some data that really isn't going to be meaningful for more than a couple of minutes, right? Like maybe the ping times for all of your servers, or whether they're up or down. If a couple minutes go by, you don't really care any longer, possibly, about what the state of those servers were a few minutes ago. And these kinds of workloads are known to be very hard on Postgres. You pay a pretty steep price for durably recording all of these state changes that, in fact, you may not really care that much about all of these state changes being truly durable. It's ephemeral data. And a final example here is if you're doing something like a large ETL process, you might be loading a bunch of data into the database and then doing transformations on it, doing cleanup, feeding it through some pipeline, and then ultimately saving it off to a permanent table. So for your intermediate tables, you might choose to use unlocked tables because you say, well, we'll just restart the pipeline if we're unlucky enough to have a server crash. So let's save ourselves some overhead and make the table unlocked. But all of this gets at the question of how much are we actually saving? How much of a benefit is there from using an unlogged table? And the answer to that question is it depends on how you measure and exactly what you measure. But just to give you an idea here, I did some benchmarking on my MacBook, and I've got one more slide with some benchmarks on a larger machine. But this is my MacBook. As you can see, the hard drive on my MacBook is incredibly slow. If you look at the number of transactions per second that I'm able to commit with pgbench, it's really tiny. I got 13 transactions per second with a single client on my Mac. That's because my hard drive is really, really slow. And every time I commit a transaction against a permanent table, I have to wait until the write-ahead log entries associated with that transaction have been flushed all the way down to the disk. And that takes a long, long time on this poor little hard drive. Okay? Very slow. When I use an unlogged table, I get 100 times the transactions per second. But most of that benefit is not happening because I'm avoiding writing data to the write-ahead log. I'm actually getting most of that benefit because the unlogged table doesn't have to wait for the data to physically hit the disk. It knows that we don't care about crash safety, so we don't really have to wait for that transaction to be flushed out to disk. So you can sort of, so I made this a three-way comparison: permanent tables, unlogged tables, and then in the middle, I have permanent tables with async commit. If this slide is a great advertisement for the value of asynchronous commit. PostgreSQL has a setting called synchronous commit. The default is on, which means we wait for every transaction to be durably flushed out to disk before we acknowledge that the transaction is completed. But for a number of years now, it's been possible to turn that off. And if you turn that off, what that means is after the transaction commits, there's still a window of maybe half a second to a second when you could lose the transaction if the database or the operating system crashed. So the transaction isn't durably committed for maybe as much as a second after it is acknowledged to the client. So you can see that just doing that by itself gives you a large percentage of the benefit of unlogged tables, especially at scale factor 10 there. You only get a couple more percentage points at most from going all the way to the unlogged table. Now, in the second set of results, on the bottom half of this slide, where you go up to scale factor 100, the benefit is noticeably more. I mean, you're now getting 23 to 29% additional performance from going to an unlogged table, because now the tables that we're testing on are a little bit larger. There's a little bit more random I/O required. The disk head's moving around a little more, and now the disk is starting to get busy. And so by going to an unlogged table, we're reducing the amount of data that we actually have to write to disk considerably. We're making the database less I/O bound, and so we're getting a noticeable performance benefit. Now, I also tried this on a 32-core Opteron system, and there the differences were much larger. Actually, for scale factor 10, there was a small regression for reasons that I haven't dug into. That's a small regression versus synchronous commit equals off. I don't really know what the reason for that is. It might be noise, or there might be some small effect there, but it's not a lot. However, you can see that in the scale factor 100 case, where I've got larger tables, I'm now getting a huge performance benefit. Even with just a single client, I'm getting a boost of 50% on my TPS rate. And as I go to 8 clients and 64 clients, I'm seeing double or triple the performance that I was seeing with just turning off synchronous commit. So here, all of the I/O that I'm saving is really helping me a lot. By avoiding all that extra writing to disk, the whole system gets much, much faster. So that's my last slide. I'll hang around and answer questions, or you can go on to the next talk. Tom?
Yeah, so did you compare with unlocked tables with fsync on? Is that another potential column you considered?
I did not consider unlocked tables with fsync equals off, because synchronous commit equals off is basically the same thing. Okay. I don't think you would see.
So the synchronous commit was off with the unlocked tables column as well?
Well, yeah, so unlocked tables, if a transaction has only written to unlogged tables, it automatically disables synchronous commit. Okay, because in that case, we know that nothing bad can happen by the commit record failing to make it to durable storage. So if you only access unlogged or temporary tables in your transaction, you're going to get that benefit even without changing the setting. Yeah. Can the table be changed to unlogged and logged back and forth? Currently, no. We haven't figured out how to make that work yet. I'm pretty sure it can be made to work, but we haven't quite figured out what the trick is there. So at present, no, unfortunately, I can't do that. I'm hoping that we will be able to add that capability to a future release. There was somebody who was actually working on a patch to add that, but we ran into some cases that we hadn't thought about. And it would actually be relatively simple to make this work if you weren't using replication, but the PostgreSQL way is not to accept half-baked features, and a feature that stopped working when you turned on replication would be pretty half-baked. So we're still trying to figure out exactly how to make that work. But I think that would be really useful. It would actually be somewhat similar to what Oracle does with their no logging hint, where like you can actually have the table become invalid in your backups, and then you have to do a new backup of it in order to to get the world back to the way that it should be. We don't have that yet. I think that will probably get done at some point, but we haven't been able to work out exactly how to make that reliable. So not quite there yet. Yeah.
What is the notable measure do you see when an unlocked table runs much faster than the other regular tables? Or where exactly you see the difference in time?
So the difference between the first two columns here is because of the latency of the disk. The difference between the second and third columns is based on the total I/O bandwidth, right? So we assume that any time you're using an unlogged table, you would also be okay with turning off synchronous commit. Because if you're willing to lose the entire contents of your table, you must certainly be willing to lose a second's worth of transactions, the last 1 second worth of transactions before a crash. So I think it's somewhat comparing apples and oranges to directly compare columns 1 and 3. The difference between the second and third columns on here is coming from the fact that there's less disk I/O. Right? So if your system is CPU bound, you're not going to see much of a benefit from unlocked tables. If your system is I/O bound and you're like, oh my God, all this I/O is killing me, I really need to find a way to reduce my I/O, that's where an unlocked table is going to bring you a benefit that you can't get in any other way. Yeah, unlocked tables is not by default asynchronous commit, it's always asynchronous commit. You never commit synchronously for an unlocked table because the only purpose of committing synchronously is to survive a crash. And when you pick an unlocked table, you're already saying, I don't care about surviving a crash. So it would be completely pointless to do synchronous commit if the only thing you've done is update an unlocked table. It would accomplish no goal. In fact, in Postgres 9.0 and prior, we didn't have that optimization. And in those releases, if you use a temporary table and you do, say, an insert into the temporary table, it will still commit synchronously if synchronous commit is turned on. And it really slows things down. You try temporary tables instead of regular tables, and you're like, man, these things commit really slowly unless I turn synchronous commit off. And so 9.1 is smarter, and it's smarter as a result of what I discovered when I was benchmarking this feature. I was like, wait a minute, this is really silly. If the data we're talking about is all going to go away anyway on a crash, there's no point in trying to make the commit record durable because losing the commit record won't cost anything. So we always switch to asynchronous mode if you're only touching temporary and unlogged tables. Yeah. So if you have a permanent table with async commit, the table will not be corrupted, but your last second or so's worth of transactions might disappear in the event of a crash. But they'll disappear entirely, right? Like either the whole transaction will be there and it'll all be done, or none of the transaction will be there and it will be as if that transaction aborted instead of committed. You'll never get corruption. So there's definitely a use case, I think, for all three of these things, right? Sometimes you may have, think about something like, I don't know, Twitter, right? I mean, I know they're not using Postgres, but if they were, they probably would not want to pay the performance penalty of doing a synchronous commit. Because as you can see, it slows things down tremendously when you commit synchronously. they would be willing to take the chance, I suspect, of losing a second's worth of tweets in the event that their whole system goes down. They don't want to lose a second's worth of tweets, but for that much performance benefit, they'd probably do it. However, they wouldn't want to go to an unlogged table because they can't possibly risk losing all of their historical collection of tweets in its entirety. That would be too much risk for them. Now, there are ways that you could jigger this to get an intermediate amount of risk, right? So, for example, you could have an inheritance parent with several child tables and have some of those children be logged and some of those children be unlogged. So you do all your updates in your unlogged table, and then every 10 minutes or so, you go and you copy the data from an unlogged table to a logged table. Well, now in your application layer, you've set things up so that you might lose up to 10 minutes worth of data, but not more than that. So there are ways to use this together with other features that we have in PostgreSQL to get sort of intermediate layers of durability, right? We can go all the way at one extreme of your tables are unlogged. If you have a crash, you're going to lose everything, to sort of intermediate points where you're going to lose data for you're going to lose a certain number of transactions, but not everything. And then on the other end, you can go all the way to synchronous replication, where you've got everything durably on 2 servers before you tell the client that it worked. So we have a huge range of what we can provide in terms of a durability guarantee, I think it's far larger than what any other database provides. Most other products are somewhere on the spectrum. They may provide a little bit of range, but we've got a much longer range and much finer grained control over it. Greg Smith gave a talk yesterday. I don't think any other product allows this stuff to be controlled in the same fine-grained way that we do, where you can actually choose per table using this feature and also per transaction how much durability you need for your data. So I think that's a really powerful advantage for us. I'm out of time. I will be happy to take more questions, but I'm going to do it in the back so I don't hold up the show. Thanks, everybody.